In this video, we're going to handle simple sprite sheet animation in a pure Unity ECS game by using DrawMeshInstanced. We're going to prepare all our data in super fast jobs and do very few draw calls in order to achieve an insane result of 100,000 animated sprites. Let's begin! Hello and welcome, I'm your Code Monkey, and this channel is all about helping you learn how to make your own games with in-depth tutorials made by a professional indie game developer. So if you find the video helpful, consider subscribing. So here's what we want to create, a nice simple sprite sheet animation system. However, we're going to be using DrawMeshInstanced, so instead of having just a handful of sprites, here it is, we have an insane amount of sprites being rendered, all of them individually animated, and if we look at the stats, you can see we have 100,000 and everything is running at 30 frames per second. So this is our goal, let's get to it. So here we are in our scene. This video is a continuation of the previous video on how to do simple sprite sheet animation. So go check out that video first if you haven't already, there's a link in the description. In that video we made some entities and set them up to use simple sprite sheet animation. So this is the result, we have entities being animated using a sprite sheet. The animation is handled by this component in here. As you can see, it stores the current frame, the total frame, the various timers, and also stores the UV and the matrix. Then we have this system in here, which is animating all of that data. It increases the time, and if needed, it increases the current frame. Then it calculates the UV and the matrix. So this whole thing is running inside a job, which means that this code runs super fast even on thousands of sprites. And finally, over here we have our renderer system. Here we're doing a for each on every entity. And we are using Graphics.DrawMesh in order to draw a mesh per every entity. We're using the material property block in order to pass values into our shader, specifically a vector4 containing our UV coordinates. So every single unit is using the same mesh, same material, the only difference is handled by the shader. Alright, so this is what we have so far, and here as you can see it does indeed work. We have our units nicely animated. However, the performance isn't as good as it can be. The limit in this system is around 12,000 units, which makes it run at 30 frames per second. That's already a pretty massive number, especially when compared to normal game objects, but we can still do better. The biggest bottleneck is here in our rendering system. We're cycling through every single entity and doing a draw mesh. So with 10,000 entities, we have the cycle running 10,000 times on the main thread and drawing 10,000 meshes. Being single threaded means this code will get slower and slower the more units we add. Now, as I mentioned in the previous video, there's another way in order to draw meshes. Instead of using Graphics.DrawMesh, we can use Graphics.DrawMeshInstanced. This function, as you can see, receives an array of matrices, so we can prepare the array containing the matrices for all of our units and the material property block for all of the UVs, and we do a single draw call. So let's try this out. Let's cycle through all of our entities. However, instead of using entities.forEach, let's make an entity query. Then let's grab our array of our animation data. Now we can cycle through our array. And here let's create our list of matrices for all of our units. So out here make a list of matrix 4x4. In here we just add them. Alright, so now we have all the information needed. So we do a Graphics.DrawMeshInstanced. We're going to use the same mesh. Alright, so here is our code using DrawMeshInstanced. So we can now get rid of this one down here. And here we have our modified code. So we grab an entity query of all the entities with our animation data. We grab an array containing all of that component data. We create and populate a matrix and a UV list. Then we create the things that we're going to need. And finally, we do a single draw call using our entire list and UV list. Okay, now let's go here in order to spawn just 10 units. And let's see. And yep, here we are. We have 10 units being displayed. And here in the stats window, you can see just a single batch and 9 saved by batching. Alright, so everything seems great. Now let's try drawing 10,000 units. And as soon as we do, we come across an error. Now, one of the limitations of DrawMeshInstanced is that it can only draw 1,023 meshes per single call. So essentially, we need to split our calls into various batches. So let's do that. Over here in our renderer, Let's define our slice count and let's put 1023 for our limit. And let's cycle through our entities. In here, let's calculate the slice size. So we're calculating the slice size since the last slice will be smaller than 1023. Okay, and now in here we make our lists. Then we cycle through our slice size, and we grab on the index starting on the I plus j, so on this slice. And finally we set our UV array, and now we can draw our mesh. Alright, so just like that, we are now going to have one draw mesh instance call per each slice of 1023 entities. Just one thing, in here we are not increasing the I by just one, but by our slice count. So essentially, if we have just 2000 entities, this will run only twice. Okay, let's see. And yep, here we are, there's no error, and our meshes are now being displayed. Alright, awesome. However, you can already see another issue specific to DrawMeshInstanced. By using this function, we are essentially bypassing all of Unity sorting and culling, meaning we must handle that ourselves. So when we create our matrix and UV arrays, we need to sort them correctly. We need to make sure that the units on a higher position stay on the beginning of the array and the ones down here on the end of the array so that everything is correctly sorted. So let's see how we can do that in the simplest and most straightforward way possible. So over here we're doing our cycle, setting up our matrix and UV arrays in order to display it. And we are doing it based on the array containing our animation data. So before we do that, we need to store this array by our entity position. So let's go all the way up here. In our query, let's also grab the translation. And in here, let's do some very simple sorting. Alright, so this should do it. We cycle through our list, and we are sorting them based on the position.y. So entities above will be behind entities below. Alright, so let's test. However, before we do that, let's go up here and test with only 100 units. You'll see why in a bit. And let's see. So here we are, and yep, everything is looking great. We have all our units animated individually, and all of them are being displayed correctly. All the meshes are correctly sorted, and transparency is all working great. So this is awesome, this is exactly what we want. However, if we look at the stats window over here, you can see why we're doing this test with just 100 units. Even with so few units, we are taking 5 milliseconds in order to run this scene. That is quite slow and wouldn't work with even a couple thousand units. So far, we've been doing everything very linearly. Here in our renderer code, you can see that we're doing all of this just on the main thread, so we're not benefiting from the job system. We're doing all the sorting right here on the main thread. This specific type of sorting will increase in complexity exponentially as we add more units. And over here, when we are creating the matrix and the UV, we're also just doing a very simple cycle going through every single unit. So now that we have the core functionality working, it's time to make it work by taking advantage of the job system and improve our performance. Over here, the biggest bottleneck by far is the sorting. Here we cycle through every single entity, and for each entity, we are cycling through every single entity. So with just 100 entities, we are essentially running this code 100 to the power of 100 times, which is already an insane number. The more entities we get, the more insane this gets. So our biggest challenge here is to figure out a way to do sorting without having to test every entity against every other entity. Now, in here, I will go over the approach that I found the best after doing a lot of testing. I don't know if my approach is the absolute best one, but the end result is 200,000 animated entities, so that's quite good. The way we're going to do it is essentially split the screen into various rectangle slices from top to bottom, and we sort each slice individually. That way, each slice has fewer entities, so it's faster, and multiple slices can be sorted at the same time. Alright, so let's get to it. Let's duplicate this system just so we have something to compare with later. So in here, just duplicate this and make this one the old system. Here, just rename it to the old one. And in here, we can add the attribute disable auto creation. So this system will not run. Okay, good. So we can now modify this one. Now in here, the first thing we're going to need is a struct to hold whatever data we're going to need in order to render. So in here, let's make a private struct, call it render data. Let's store a reference to our entity. We're also going to need a float3 for the position. And we're also going to need the matrix and obviously the UV. Okay, so this is the struct that we're going to work with inside all of our jobs. We need the position for sorting and the matrix and UV for rendering. So let's start off with the job to split our entities into just 2 slices. So we're going to have a job cycling through all our entities, grabbing their position and animation data. Now in here, the way we're going to split our entities is by using native queues. So we're going to have 2 fields for each queue. We're using concurrent so we can concurrently write in various threads. Now the goal in here is essentially if an entity is on the top half of the screen, it will be placed on the native queue 1. If it's on the bottom, it will be placed on the second one. So we also need to know where exactly is the top and the bottom. So we've got a float for the top part of our screen, a second slice counting from top, so in this case it's going to be right in the middle, and the bottom of our screen. The reason we're not simply defining the top, middle, and bottom is because later we're going to slice it into more than just 2 parts. Now in here, inside our execute method, first we do some simple culling to see if it's even within these values. So we have our valid position if it's above the bottom and under the top. Now if it is valid, we just do a very simple if. Alright, so here we have very simple. We create our render data based on the information in here. Then we simply check if it's under the second slice, then we place it on the second queue. If not, we place it on the first queue. Alright, so that's it. This is our very simple job. It simply goes through every entity and places it on one of 2 queues. So at the end, we have our entity sorted into either the top or the bottom half of the screen. Now let's run this job. Let's go down here into our update. And first we're going to make our queues. So we have our 2 queues. Now we need to calculate the slice values based on our camera. So we grab the main camera, the camera position, we calculate the bottom based on the camera orthographic size, same thing for the top, and then our second slice, which is right down the middle. Alright, now let's schedule and complete our job. Alright, so we are creating our job, passing in all the values that it needs, schedule and complete. Okay, so let's do a very quick test. Let's do a simple debug.log to see how many entities are on the first slice and how many on the second slice. So a debug.log, native q1.count, and same thing for the 2. Alright, let's see. And yep, here in the console we can already see 4654. So we have 46 entities on the top half of the screen and 54 on the bottom half. Okay, great. So we have correctly split our entities into 2 separate slices. So essentially, right now we can sort both slices at the same time. And since each of them has fewer units, they run even faster. So you can already see where we're going with this approach. So after doing all of our slicing, we now have 2 queues, 1 for each slice. However, we can't directly sort a native queue. So we need to take these queues and convert them into native arrays that we can then sort. So let's make a job to do just that. Alright, so here it is. Very simple job. We take a queue, we take an array, we try to dequeue whilst the queue has elements, and we simply place them on the array. So very simple. Now let's run our job. First we need to create our arrays. For the size of the array, it will be the same size as the queue. So we go into the queue and we grab the count. Alright, here it is. So we first define our arrays with the same size as our queues. We create our jobs. We schedule the jobs and put the job handle in a job handle array. And once both of them have been scheduled, we complete both jobs at the same time. So right now, down here, we already have 2 arrays instead of 2 queues. So with those, we can now sort them. So let's make a job to do just that. Let's sort the same way that we did previously. And now let's run both jobs. So over here we now have our both arrays correctly sorted. Now all we need to do is draw them. So down here, let's get rid of our previous sorting. And in our draw code, let's modify it to be more efficient and work with simple arrays. Let's make it work with a matrix and UV array, so no references in the animation data. So in here, in order to create a new matrix array, we need to know essentially how many units are visible. Since we're doing culling, not necessarily every single entity will be visible. So let's calculate that. Do an int for the visible entity total. And here it will be essentially the total of our native array 1 plus native array 2. So we create an array of that size. Now let's draw our entities using these arrays. So let's assume that these arrays are completely filled with all the entities. So inside we no longer cycle through our animation data. Instead we make some basic arrays out here. So we have these 2 normal arrays, and now inside our cycle we can simply use a copy to. So we use the function on the native array, and we copy from our source native array. So that's the matrix array. And here we can pick the source index. So we are using this superfast function in order to capture slices from this array. And then we just draw our mesh. Alright, so this is it. Let's also remember to dispose of all our native arrays. So now we have our draw code in here working perfectly based on these 2 arrays. So in terms of the drawing, we don't care what happens previously, we just care that we have these 2 filled arrays. Now all that's left is in order to take our sliced arrays and merge them into these 2 arrays. So let's make a job to do that merger. Let's go up here, another private struct. This will be the fill arrays. Alright, so here in our job we have our origin native array and the matrix and UV array, which are the full arrays. Then we also receive a starting index. So the first array will be on a certain index position, then the second array will be on another starting index position. So since we have multiple jobs writing to both of these arrays, we need to disable the container safety restrictions. And this attribute is also inside Unity Collections low level unsafe. Now when using this, you need to make very sure that you are very careful with your indexes. You need to be careful to not cause any race conditions. So now let's run our job. So down here we have our 2 arrays sorted, then we create our matrix and UV array, and it's in here that we need to fill them up. So we have our 2 jobs in order to take our native array 1 and 2 and place them in the matrix array and UV array. Again, very careful with the starting index. As you can see, the first one won't start on the starting index of 0, but the second one won't start at the end of the index for the first array. So after this, after these jobs have been completed, all our data is now sorted and placed in a single full array, one for the matrix and one for the UV. Now in here we wrote a lot of code, but hopefully this was easy to follow along. The strategy behind it is quite simple. So the first thing we do is we have a job in order to cull and sort our entities into various slices. So in this case, we just have two slices. So one for the top part of the screen and one for the bottom part of the screen. So this job places our entities in the correct queue. Then before we can do sorting, we need to take the entities from that queue and place them in an array. So we have this job to do exactly that. So down here, we now have our two arrays ready. So we have this job in order to sort our arrays by position. So we schedule both jobs and then we run them both. So essentially the top and the bottom will be sorted at the same time on different cores. And then once we have them all sorted, we create full arrays for our matrices and our UVs. And then we have this job which takes our individual arrays and merges them all into one single array. And finally, when we have these two arrays all filled with the correct data, down here we have our draw code. So we go through our arrays in slices of 1023, since that's the limitation of DrawMeshInstanced. We do a simple copy from our full array into our slice array, and we render the whole thing. And obviously one thing we can do in order to get extra performance is to simply add our burst compiler into all of these jobs, since all of them are burst compatible. So add to that one, that one, that one, and that one. All right, so let's see. All right, so here we are with our new system and all of our entities are being drawn. So the code is working great. Now it's time to see exactly how much of a speed difference we made between the old system with no multi-threading and this one with multi-threading. So here we have the old system running with 500 units and as you can see 100 milliseconds per frame. Now let's see the new system. And here we are with the new system rendering those same 500 units in just 1.5 to 2 milliseconds, thanks to all the benefits from multi-threaded code. Okay, so this is already pretty awesome. Now, over this past week, I've spent a lot of time working on this code and making it run as fast as possible on every single step of the way, so let's see the absolute best performance I've managed to get. So here is the final system running, and over here you can view the stats. As you can see, we have 100,000 individually animated sprites running at 30 frames per second. So this is pretty much the definition of insanity. So let's see how this final system works, and you'll be able to see the same structure that we built. The strategy in here is very much the same. We have the camera viewport being cut into multiple slices. However, instead of having just 2 slices, we have 20. So in here you can see our cull and sort job. We have our 20 slices and 20 queues and all of these ifs in order to place everything in the correct queue. And we are also culling for the X minimum and maximum. So over here in the scene view, you can see the culling in action. As you can see, all of them are being drawn, but if I move the camera, as you can see, the entities that go away on the culling on the minimum X, they get hidden, and same thing on that one. So it only actually shows the entities that need to be shown. So we have our job using our 20 slices. And here we have our update. We are going through our position slices, which are 20, getting the camera and calculating all of these slices. Then we create all the arrays based on those slices. We use the same native queue to array job in order to convert all of those queues into all of those arrays. Then the same thing in order to sort. Then we have our individual arrays. We put together all those 20 arrays into 2 separate arrays. And then we have our simple draw code. So as you can see, the structure is very much the same that we did, only with a bunch more improvements so that it runs insanely fast. Again, here we have 100,000 individually animated sprites running at 30 frames per second, and we can also look at the profiler. So here we have our profiler. As you can see, everything is running insanely fast. And that's it. Here's our insanely fast, simple Spreadsheet animation system. As always, you can download the project files and utilities from unitycodemonkey.com. If you liked the video, subscribe to the channel for more Unity tutorials. Post any questions you have in the comments and I'll do my best to answer them. Alright, see you next time.